Okay, so that's sort of a brief tour of the memory technologies that are available to us as engineers. Now what we're going to do is say, well, what is it we want, right? We have a choice of these capacities, these technologies at this end, which are very inexpensive, and we can afford to buy, billions and trillions of bytes of information. But we want our computers to run very fast, and so it seems like we're going to be stuck having to spend lots and lots of money on the fast memories. And so what we really want, if we could somehow arrange it, is the best of both worlds. Okay? We want a very big memory that's also very fast. And we can almost get our wish, surprisingly enough. And what we're going to do is spend some time working on the technology that will make our wish come true. And as you can imagine, the scheme we're going to use is going to use sort of a hybrid, which is a combination of these small but very fast memories and large but very slow memories. And what we're going to hope to do is to get something that is both big and fast. And statistically, that will turn out to be true. And so we're going to sort of rely on some statistical arguments about the sort of, what addresses we ask for in which order. And by looking at the statistics of memory accesses, we're going to be able to engineer a system that, on the average, does very well. In the worst case, it suffers from the big memories being slow. But on the average, our system will perform quite well. So let's sort of explore that for a bit. So the key idea, which I'll say now, and we'll look at in a graphic representation in the next slide, is that when you think about how a computer operates, it mostly is not asking for addresses willy-nilly. For instance, think about how the program counter is going through memory, right, as we're fetching instructions. Mostly it fetches instructions one after another. And occasionally there's a branch, maybe often back to an instruction, back to the beginning of a loop, so back 10 instructions or so. But there's a certain orderliness to the access patterns. And in fact, there's what we call locality of reference. If I look at the amount of the references that are made by the computer over some span of time, if I reduce that span of time to a small region of time, on the order of tens or hundreds of instructions, I'll discover that the number of memory locations that I'm trying to access is actually very modest. In other words, I tend to ask for, if I'm asking for memory location at location X, in the next cycle I'm very likely to be asking for the one at location X plus 4, particularly if it's instructions. And because of looping and behavior of our programs, if I've asked for an instruction in the past, chances are, there's some probability, a reasonably good probability, that I'll ask for it again in the not too distant future. So we're going to take advantage of that. So let's look at some possible memory reference patterns, and this is sort of a very schematic diagram of trying to sort of plot memory references versus time. So if I think about a program, a program that has loops and subroutine calls and things like that, I might expect to see a reference pattern that looks like this, where the addresses sort of increase as I execute instructions sequentially. I might jump back to the beginning of the loop and execute that loop several times. Occasionally I might branch forward in my program, an if statement, something like that, and skip over a couple of instructions. I might make a subroutine call and go off and to some entirely new region of memory. So that sort of represents a discontinuity in my nice orderly sequence of addresses. But once I'm past that discontinuity and I'm in the body of the subroutine, it becomes orderly again. Okay. Occasionally it gets higgledy-piggledy. Particularly if you're doing, method dispatches on objects in an object-oriented programming language. But by and large, this is not just random access. There's some orderliness to the accesses. That holds even more true of the stack. And almost invariably, we're accessing the local stack frame. As we do procedure calls and stuff, the stack frame grows, where we stack rows, and we might access a new stack frame. But in general, we're accessing a very small region of the stack at any given moment, the activation record for the current procedure. And in terms of data accesses, we're accessing structs in memory, or perhaps stepping through an array. In some cases, as shown here, we may in fact be copying from one array to another. So we might have a couple a load and a store, where the load comes from one data structure and the store goes into another data structure. But it's not like that most programs have a certain systematic way in which they're dealing with particular objects at a particular time, or dealing with a particular part of the array at a particular point in the program. And so if you put all this together, you can see that in a particular span of time, the actual number of dots, the range of addresses that appear here in the blue region is actually limited. There's a limited number of program locations and a limited number of stack locations and a limited number of data locations that I'm accessing. So that's what we mean by locality of reference. Okay, and in fact, if we make that blue region wider and wider and wider, and say, well, if things are not well behaved, the wider we make it, the more locations we would expect to be accessed. But in fact, for most programs, you'll discover that the number of locations that are accessed, for any given width of that blue region, for any given sort of little span of time, at some point, it dramatically drops off. In other words, even though I could double this blue region, at some point I won't double the number of memory locations that I'm accessing because of looping, and I keep using the same data structures, and I keep referencing the same stack frame. So even though I'm considering a longer span of time, I'm still working with the same old memory locations. And that is going to be the key to our engineering trick. Okay.